Hello, my name is Michael Johns. I want to give you a walkthrough of my final project for CSCI E89 Deep Learning Spring 2019. This is a project categories detection and disambiguation in free text using GDELT data. So the project has 6 notebooks. They all have kind of a flow that starts with an introduction just to set up the data. And also then the data itself has metadata associated with it that gives you some benefits that we'll get into. And then from that metadata, we're able to crawl against the URLs that are referenced as part of the collection. And ultimately go through some normalizing stages, ultimately finalizing to a master data frame, so to speak, and then do some modeling in the 6th notebook. So the data set is called GDELT. It is a global data source. It publishes on the order of hundreds of thousands of articles and various feeds from around the world on a daily basis. And that can add up pretty quickly. So it's a really great source for worldwide news and topics of interest. The data that we'll be looking at is the data set around 2017. And earlier in 2017, in March, there was an attack on Parliament, and then there was a second attack in May at an Ariana Grande concert. And that attack occurred on the 22nd. So we're going to look at just what the news was around that time, 22nd through the 24th. And so 3 days worth of data, and then filter that accordingly for our purposes. The libraries that we use are Spark, so able to take advantage of cluster capabilities with Spark. We're going to use Spark NLP on top of that for part of the standardization, normalizing of the data. We'll use Gensum, Scikit-learn, and Keras as well. The URL at the bottom is where the data came from. Within that, you can get, for the time period that you want, you can get the data there. Most of these notebooks can run on CPU hardware. I mean, they all could, but up until the last notebook, the 6th notebook, CPU hardware is fine, but GPU hardware performs better for the last notebook. So when we look at the metadata, you get a combination of information. You get some information that has a document ID associated with that entry in GDELT. You also get a set of exploded information or columns of information that could be exploded around organizations, persons, themes, sources, persons, if I didn't say that. So you have this extracted information that actually plays really well to understand what GDELT understood to be meaningful entities within the data. That has implications for potentially turning that toward labeled data as well in certain model training and sort of supervised scenarios that would be useful. Now the data has, for the 3 days, has about 1 million documents. What we do is we filter that down to just the Manchester data, Manchester, UK, and that gives us a starting corpus of about 82,000 documents. So from that metadata, the fairly substantial effort to crawl that information. I have the benefit of having crawled this data in the past. So for this project, I didn't have to start from that point, which was a pretty big task. So I was able to start from the previously crawled data, but everything from that point forward is fresh to this project. So the data's crawled, it's cleaned up. There's some filtering around just various things that happen in the data to get down to that text column that you can see in the upper right has the main information that would be the article content itself. So to normalize, we go through really several stages. We go through document assembler, sentence detector, tokenizer, stemmer, and then a normalizer and a finisher. We're using Spark NLP. That's a John Snow John Snow Labs provided library. And we break it up in the middle to do some things around sentences as well. So once we get to the sentence stage, that's a machine learning pipeline that allows us to kind of split the data conceptually a little bit and have two separate focuses on normalizing. One is at the document level to have one single vector for the document, and the second is to have sentence level vectors as well. So in thoughts around normalizing, it's really around the outliers, so skew around documents that have massive numbers of sentences relative to the rest of the corpus. So you're talking about some that have, many thousands of sentences, and then others will have much less. So kind of on the outset, just figuring out where the right point is, and as you look at the chart, it really brings you down to around 250 is a good number of sentences in a document to kind of cut off that as a threshold to have kind of a better representation of apples to apples when you're doing vectors. And not shown here, but within that there's actually length of sentence as well. So some articles publish without any punctuation for whatever reason. They really provide a lot. The way it was scraped, I think, has to play with this. But they give you a lot of length of sentence in a way that really throws off your vectors. So also not shown, but filtering out the long sentences in addition to the documents with large numbers of sentences, kind of shaping that to have something that's a bit more balanced. So we do apply stop words, and we do some things around text to vec. The word to vec that I initially used was the Spark version. I thought through and went after it a few different ways, but ultimately I really picked up after the stop words in the final phase and ultimately in the document modeling notebook. So focus more on the stop words and then use Jensen ultimately for word to vec. But we do have the Spark vectors there. So there's several fields that were built early but not ultimately used. So in the finalized stage, we have this great entity information that's been extracted in the metadata side. So the thought was to filter highly occurring entities and only keep those highly occurring entities. So those are entities that appear 4,000 times or more in the corpus. And with that, whenever you filter at that level, this means these are widely used when you think about labeled data. We had 2 million themes, 300,000 persons, 80,000 organizations, and 4,000 sources. So still a lot of information appearing 4,000 times across this 80,000 document corpus. So within that, it made more sense when you think about TF-IDF, basically concepts around persons and organizations. We don't really want to use that for categorization. But the great thing about GDELT is they actually give us themes. So it actually does make sense to use highly occurring themes. And so from that, I focused on the top approximately 150 themes based on a threshold that I used to determine that. And ultimately, I derived 10 categories using PCA. I could have used LDA as well, but I used PCA to give me 10 categories. So I do have labeled data. Now, the way this ultimately played out is I did not use the labeled data in the model that I ended up building, but it would be available for subsequent efforts. So that all that data was joined back to have kind of a single data frame to incorporate that theme type data that we just talked about. And then on the crawl data, more work was done there. Essentially, we had a file name that encoded the record ID and the source from which it came. And so by doing a little bit of parsing on that, we were able to have a join. Those two together actually are both important for joining. So I was able to join the crawl data frame back to the metadata data frame in a way that allows to have one single master data frame. So that's what this shows here, is just that final preparation as we look at the topics. So we have the 150 topics that go with the most important ultimately for labeled data. And then we move to the document model. So we used Word2Vec in Jensen, and kind of the standard at the top part, just the standard Jensen concepts. But then we transitioned through that, and hopefully I can show it briefly at the end. If not, it'll come up in the report, of course. But we transitioned from the standard toward a matrix that was able to then be used as input data to a Keras model. So the vectors that we built turn into a matrix that becomes the input to Keras, and then we're able to do a actual word and a predicted word in a batch mode with the Keras model. So just we use the Word2Vec capabilities, just using it to disambiguate, get some similarity scoring, looking at what words are most similar to Arianda, Ariana Grande was the singer where the attack occurred. So when we look at similar scores for Ariana, we see that there's a couple of misspellings of her name. So from a disambiguation perspective, that can be used to be able to identify similar content, maybe look at other aspects in Ariana's vector to understand if maybe there's other characteristics or kind of similarities, cosine similarity scores that can be used to say, okay, this is actually the same Arianda, and be able to conceptually or logically join those two together. Then we look at Albidi in this screenshot. He was the actual perpetrator of the attack, so we can see some things about him, that he's affiliated tightly with Libya and Islamic Brotherhood, things like that. So we did a plot using scikit-learn against the Word2Vec using TS&E, and we're able to see on the early 1,000 words, we're able to see very, very tight clustering around the early words in the document, in the vocabulary, and then you see it spread out as you move away from those very early words. And that's what you expect in the ordering of the vocabulary. It's ordered by importance. So that comes through in the way this scatter plot shows. When we look at the 1,000 words, you're at the end of the vocabulary, the last 1,000 words, and we see within that, we see still a tighter grouping in the middle with more scatter around, but it's not nearly the same as the early 1,000. So we did a lot inside the actual notebook. This will come through in the report, but we predict against the word provided using Keras. We come back around and then we calculate kind of from the data that came out, the NumPy array that comes out. We're able to calculate similar words and use that to understand how the model performed, how the prediction performed. And so we're only just showing a little bit here for brevity. But when we break that out and we look at it from an accuracy perspective and looking at the similarity scores that come out of the model, on the top 20, we actually got 100. If we look at the first 20 words of the model, we got 100% accuracy, no misses. In fact, that shows up on the chart on the left. When you look at the chart on the right, the scores are very, very high on the predicteds, up close to 100%. And then it tails off pretty quickly for all of them for that next word. The next word kind of falls closer to that 80%, sub 80%, and kind of hangs around there, but doesn't, you know, kind of each one has a little bit different story in terms of the word and how the top K similarity words coming back, how they score. Now, when we look at that on the bottom 20 words of the vocabulary, we do see a different story. So when we look at that, we see that we actually have 2 misses in the top 20 that aren't able to accurately hit the predicted word matching the actual word. So we have 2 misses there, indicating the weakness of those. And then we look at the predicteds, and we see a much more of a scattershot performance across from the first top end all the way through to the 5th top end, which is the number of words we considered. So for next steps, you know, we could assess sentences instead of the document level. So that would be on the table to take the same concept and do sentence level and see if we get tighter vectors. We could also build another model that can predict using the labeled data, that PCA data. We could also do some sort of generative, you know, context-aware style, like an RNN, an LSTM flavor, where we're able to give predictive content based upon that contextually aware history. Or we could follow up with other techniques. There's interesting papers out there around, you know, pure disambiguation concepts, like the classic concepts around like name and addresses. So we could try to apply this to a data set like that and maybe extend the approach. Anyways, thank you for your time. That concludes my run through.